In this second module of the chapter 1, in module 1.2, I will cover population characteristics and metrics. Demography is concerned with four aspects of populations. First, size, that is the number of individuals in the population. Second, distribution, the arrangement of the population in space at a given time. Structure, the distribution of the population with respect to age, size, gender, and so forth. And change, the variation in the size, distribution, or structure of population over time. Population size. This refers to the total number of individuals. We have de facto population, where individuals are located, and de jure population, which is the actual residence of individuals. These terms and concepts obviously were created in the context of human population studies, but at least in principle, these could also be applied to populations of some non-human species. Population distribution. Number by spatial location, by central location, by standard distance. The number by spatial location, where, for example, the number of individuals within a 1 kilometer square region are distributed by 10, 20, 30, and 40% in these four different hypothetical subregions. We have number by central location, where N denotes the number of subdivisions, Pi, the number in the population at point I, and Xi and Yi at horizontal and vertical coordinates, respectively. Note that the sums of these algebraic relationships will yield the central location for the aggregate in XY coordinates. We have number by standard distance. If X and Y are the coordinates of the population center from the formula just presented, then the standard distance D is given by this formula, where Fi denotes the number of organisms in a particular region, and N equal the sum of the Fi individuals. This is the formula for the spatial version of the familiar formula for standard deviation. We have population structure. This is the structure of a population is the relative frequency of any enumerable or measurable characteristic, quality, trait, attribute, or variable for individuals. These items include primarily age and sex, but can also include characteristics such as weight, length, shape, color, biotype, genetic constitution, birth origin, and spatial distribution. But only age and sex will be covered here, since these are the most common traits by which individuals within populations are decomposed. An age pyramid is often used to illustrate the age by sex distribution of a population. Here is an age pyramid depicted as a set of horizontal bar graphs with number on the x-axis, age on the vertical or y-axis, and the number of males and females on the left and right, respectively. Next, we have sex ratio, denoted SR, with subscripts M and F denoting the number of males and females, respectively. Sex ratio is computed exactly as it sounds, in which SR equals the number of males over the number of females. And the proportion males, denoted PM, equals the number of males over the total number of males and females. Age frequency is computed as follows. Let the subscripts M and F denote males and females respectively. Then the frequency of males age X equals the number of males at age X divided by the number of males total. And likewise, the frequency of females age X equals the number of females at age X over the total number of females. Population change in size can be expressed in several ways, including as a linear change, which is a change in amount. In this case, the number at time t minus the number at time t plus 1. A second way is as a ratio, which is the change factor, where you have n at t plus 1 divided by the number at time t. And a third way is a fractional or proportional change in the population, which is the difference in the number at t plus 1 and the number at t divided by the number at time t. A linear population change occurs when the difference between the numbers in a population of two time periods is a constant. For example, the sequences 2, 4, 6, and 8, and 10, 20, 30, and 40 are both linear series because the constant differences in the series are 2 and 10 respectively. The recursive formula for this linear change is thus the number at time t plus 1 equals the number at time t plus c, where c is the constant difference. A geometric change occurs when the ratio of the numbers in a population of 2 time periods is a constant. The sequence 1, 2, 4, and 8, and 10, 100, 1000, and 10,000 are both geometric series, since the ratios are 2 and 10 respectively. The recursive formula for here, geometric change, is thus the number at time t plus 1 equals c times the number at time t, where c is the constant ratio. The general formula is the number at t plus 1 equals the number at time 0 times c raised to the tth power, where n0 is the initial number. We have population change in space. Every move is an outmigration with respect to the area of origin and an in-migration with respect to the area of destination, the balance of which is net migration. The sum total of migrants moving one direction or the other is gross in-migration or gross out-migration. The sum total of both in and out migration is turnover. A group of migrants having a common origin and destination is termed a migration stream. The difference between a stream and a counter stream is the net stream, or net interchange between the two areas. The sum of the stream and the counter stream is called the gross interchange between the two areas. Migration rates. Let M, I, O, and P denote movers, in-migrants, out-migrants, and population at risk, respectively. Then the mobility rate, denoted MR, equals M divided by P. The in-migration rate, denoted MI, equals I divided by P. The out-migration rate, denoted MO, equals O divided by P. The net migration rate equals I minus O divided by P. Note that P is the common denominator across all these migration rates. This ends Module 1.2.